Welcome back. In this section, we'll be talking about the graph of a function. We've already talked about graphs of equations. If you have an equation involving x's and y's, then the graph of that equation would be all of the x and y points that satisfy that equation. And the same thing is true for graphs of functions. If you have an equation that defines a function, if y is a function of x and you've got an equation involving x's and y's, then the graph of that function will just be all the points that satisfy that equation. So that part is the same as before. The difference that we're interested in here is the difference between what any graph of an equation might look like versus the graph of an equation that's also a function. And this is where we'll need to remind ourselves that for something to be a function, that means that every input value should map to exactly one output value. So every x should match up with exactly one y. That means that you wouldn't be able to have something where, let's say, you had an x value of 3, where you've got a point that has a y value of 4 on the graph, and also you've got an x value of 3 where there's also a y value of -3 on the same graph. That would be something that you wouldn't see in the graph of a function, because that would be something where you have one x value where there happened to be more than one y value that it maps to. So this would be an example of something that you wouldn't see on a function. And as far as the graph goes, that means that if I were to draw a vertical line through that x value, through the x value of 3, it would pass through my graph in more than one point. This is what I would say is called failing the vertical line test. The vertical line test would be where we try to see, would we have a vertical line that crosses through our graph in exactly one point, or are there vertical lines that cross our graph in more than one point? If you have what I've got here, a vertical line that crosses through your graph in more than one point, that means you don't have a function, because that means there would be one x value that has two y values or more that correspond to it. As opposed to something that is a function, and for that would be something where every x value only matches up with one y value. So for one x value, you might have one y value and only one y value, which means that the vertical line you draw through that x value should only pass through one point. That's our vertical line test. So if you have a set of points in the xy plane, if that's the graph of a function, it's the graph of a function if and only if every vertical line passes through at most one point on the graph. It could pass through nothing, and there's reasons for that as well. So for example, you could have something where the domain is just the values of x that are 0 and larger. So for example, something like our friend y equals square root of x. That would be a function because vertical lines pass through the graph of that equation in exactly one point. And it's also true that you could draw a vertical line that doesn't pass through any points, and that's because that's a part of the graph where the function at y equals square root of x is not defined. So to be a function, vertical lines have to pass through at most one point. But if you pass through if any vertical line passes through more than one point on the graph, then it's automatically not a function. So that means if we're thinking back to chapter 2, when we graphed an ellipse, that would be something that would not be a function because vertical lines would pass through those in two places. Similarly, for equations of circles, when we graphed those would not be functions for the same reason. Vertical lines would pass through them in more than one place. But there's lots of graphs that we have seen in our past and will see in the future that do have that property, that they are graphs of functions. So for this little function that I've got here, the reason why we can feel confident in saying that it's a function is it passes the vertical line test. You can see that any vertical line that I draw is going to pass through this graph in at most one place. It could pass through no places. For example, if I drew a vertical line further to the right outside of our domain, sure. Or further to the left outside of our domain, sure. But there's no place where I can draw a vertical line that passes through 2 points or more. Now, I know you might be looking here at these 2 points and saying, well, what about them? What about a vertical line that passes through those? And you would be wrong to think that we're passing through 2 points on our graph, because the distinction between how I've drawn them is this. 1, 2, I've drawn that as a filled in circle. This is a point that is actually on the graph of my function, or graph of my equation. As opposed to a hollow circle, we use that to indicate points that are not on the graph. So that means that if you're thinking about what happens when x is equal to 1, although you might at first glance think that there are 2 different y values, when x is 1, there's only one y value, and it would be the y value of 2. The point 1, 1 is not a point on the graph, so when x is 1, y is certainly not 1. That also means other places here on our graph, we've also got some holes going on. For example, this point here, 3, -1, that is not a point that's on our graph. So that means there is nothing going on this graph when x is equal to 3. There is no y value happening when x is 3. There's nothing there at all, period. Similarly, for x being -3, there's a hole there as well. There's nothing on the graph when x is equal to -3. One other thing just to note here about the way that this graph has been drawn, the endpoints are not arrows. Sometimes we'll have graphs where, let's say at the end, we might have an arrow, and that would indicate that the graph is going to continue in that direction forever. Here, though, I've got my graph ending in a dot, telling me that that's where we end, that there's nothing after that, that it doesn't continue on in this direction. And same thing on the left side, that filled in circle, that's telling me we're not going to continue going up forever. The graph stops here. There is no point -3, 5. We get close to, very, very close to that point, but that's where the graph ends. And that's important to think about here, because when we're thinking about the domain and the range, we have to think about what are the x values that we're using. And so for our x values, we don't have anything less than -3. We don't have anything larger than 5. All of our x values are between -3 and 5. But we're going to have to be a little bit careful, because there are some values that are not included. The -3 is not included. And in the middle of things, you can see that the value of +3 is also not included. So if you're thinking about what values of x can we can have everything from -3 up to 5, but we're not going to include the -3. We're also not going to include the +3. +5, however, will be included. So if I'm trying to say what my domain is, and if I wanted to write that in interval notation, I'd say for my domain, it's everybody from -3, not including it, up to +3, not including it either, together with everybody between 3 and 5, not including the 3. However, I do want to include the 5. So for this function, my domain is everybody between -3 and 3, and also everybody between 3 and 5, and including the 5. For the range, this is just the set of all the y values that we observe. And if we're looking at our graph, you can see that there's graph going on for y values of -1 up to +5. However, the -1 as a y value is not included, because the point 3, -1 is not included. And 5 is also not included, because that point -3, 5 is not included. All the other values in the middle, however, are. You can see that even though I don't have the point 1, 1, I do have a point that does have a y value of 1, so y value of 1 shows up. And in fact, we've got y values between -1 and 1. We've got y values from 1 and larger. So we have y values going all the way from -1 up to 5. Not including the -1, and also not including the 5. Now b we've already answered. What is f of 1? What's the y value when x is 1? We know that for that, the y value when x is 1 has to be 2, because again, looking at these 2 points, 1, 2 is the point that's a filled in dot. That's the point that's on the graph of our equation, whereas 1, 1 is not. Part C is looking for where is f of x equal to 0. In other words, where is the y value 0? Remember that f of x is the same thing as the y value for our function. So when we say, for which x is f of x equal to 0, we're really asking, where is the y value equal to 0? And looking at our graph, there's 2 places where the y value is 0, when x is 2 and when x is 4. So if you were solving f of x equals to 0, the solution set would be 2 and 4. And then finally for D, for which values of x is f of x less than 0? Where are the y values less than 0? Well, it's all of these y values between y values between x being 2 and x being 4, but we'll have to be a little bit careful. Number 1, we want it to be less than, not less than or equals to. So that means I wouldn't be including the 2 and I wouldn't be including the 4. But I also can't include the 3 since that point is not part of the graph. So where are we below the x-axis? Well, there's the part that's between x being 2 and x being 3. And then there's the part that's between x being 3 and x being 4. So for which values of x is f of x less than 0? Everybody from 2 to 3, not including the 2, not including the 3, and everybody from 3 to 4, not including the 3, not including the 4. So the 3 was not included because that's not a point that's on our graph. The 2 was not included because that's where we're equal to 0, not less than. The 4 was not included for the same reason. That's where we're equal to 0, not less than. So where is f of x less than 0? Between 2 and 3, and also 3 and 4. X-intercepts and y-intercepts, there's not really any big surprises here. We've talked about intercepts before. We know that if you're thinking about x-intercepts, that's where something crosses the x-axis. That's where the y value is 0. And of course, f of x is the same thing as the y value. So if you want to find the x-intercepts, you're going to need to find out where is y 0, or in other words, where is the function f of x equal to 0. If you're thinking about y-intercepts, that's where you cross the y-axis, and when you cross the y-axis, the x value is 0. So to find the y-intercept, you just need to evaluate what is f of 0. What's the y value when x is 0? I have a little bit of a side note here that functions could have no x-intercept, maybe only one, maybe multiple, maybe infinitely many, as we're going to see in trigonometry. But for functions, they can only have one y-intercept. And the reason that they can only have one y-intercept is because if something were a function and it had two y-intercepts, then that means you would have something that failed the vertical line test. So couldn't actually be a function then. So if you want to be a function, you can have at most one y-intercept. It's also possible that you could be a function and not have a y-intercept. That's another possibility. So for example, something like this function, the horizontal line that has a y value of 3 and starts when x is 1 and larger. So something like this, where it's uh, starts at 1, 3 and continues to the right, that never crosses the y-axis. That has no y-intercept, it has no x-intercept, but it definitely is a function. However, you couldn't have two y-intercepts. You can have 1 or 0, but that's it. Those are the only options that are available to us. So for something like this, f of x, we're going to find our intercepts eventually, but before we do, we're going to think about our domain. And before I do that, I'm going to simplify my function as well while I'm here, and that means factoring. Numerator factors nicely, x minus 2x plus 1, and the denominator factors nicely as x minus 2, x minus 5. And that means that f of x actually could be simplified. It could be simplified as x plus 1 over x minus 5. So that means when we're thinking about finding x-intercepts and y-intercept, we can actually deal with the simplified version of f of x rather than the original version of it. Now, the one place where we do need to be careful here, and this is, again, why I said we're going to state our domain first, is that canceling things out doesn't change the domain. If you're thinking about the original function f of x before I did any canceling, you would have said for the domain that it would be the set of all x's such that x can't be 2 and also x can't be 5. And even though we canceled out the x minus 2's, that doesn't change my domain. My domain would still be x can't be 2 and x can't be 5. So even though you might look at this and say, oh, I could put in a 2 for x if I felt like it, the reason you can't is because the original function would have been undefined when x is 2, which means the simplified version is also undefined when x is 2. So feel free to simplify your functions. Just remember that that's not going to alter what the domain is. Okay, so now let's find our x-intercepts. And for this, again, I'm going to be using the simplified version. And that would be, if we want to find the x-intercepts, we want to know when is the y value 0, or when is f of x equal to 0. And that's easy enough to solve. X plus 1 over x minus 5 equal to 0. And a fraction can only be equal to 0 when the numerator is 0. And so that means that x needs to be negative 1. So we only have one x-intercept. And the x-intercept is the point negative 1, 0. Do remember that intercepts are points. So when I say what is the x-intercept, it's the point negative 1, 0. If you just say that the x-intercept is negative 1, that's telling me the x-coordinate for the x-intercept, but the actual x-intercept itself is that point, negative 1, 0. Now, I do want to say that if you had decided to use the original function, so what if you decided to not use the simplified version, you decided to use the original function and solved for where is f of x equal to 0? Well, then you'd have this fraction being equal to 0, and of course, a fraction can only be equal to 0 when the numerator is equal to 0, and you might be tempted to say, oh great, x can be 2 or x can be negative 1. But that's the reason why we always think about our domain first. 2 would be an excluded value, so even if you were dealing with the non-simplified version of f of x, you still would not be able to conclude that 2 is the x-coordinate for an x-intercept, because 2 is not inside of our domain. So regardless of which version you use, whether you're using the simplified or the unsimplified version of f of x, you again are going to come up with the same result, which is that there's only one x-intercept here, and that's the point negative 1, 0. So next, finding the y-intercept. And then just a little question to remind ourselves, how do I know that there's only one y-intercept at most? Notice the way that I phrased the questions. The first one in B, I said find all x-intercepts, plural, so it's possible that there could have been more than one. But in part C, I say find the y-intercept, that there's only one y-intercept. And the reason why I know that there's only one y-intercept and why there couldn't be more would be, number one, the reason why there has to be a y-intercept is 0 is in the domain. That means that 0 as an x value could be put in, which means since it's a function, you will get one y value as a result. And that's the reason why you couldn't have more than one y-intercept, because if you did, that would have meant that you would have had two y values matching up with that one x value of 0. So we know that because 0 is in the domain, we are definitely guaranteed that there is a y-intercept, but because it's a function, there can't be more than one y-intercept. Otherwise, we would fail the vertical line test and we would have something that's no longer a function. So now all we need to do is solve to find out what is the y-intercept. And remember, the y-intercept happens when x is 0. So we're going to let x be 0, and same thing again, you could use either the simplified or the unsimplified version of f of x, and it will lead you to the same value regardless. We know that we can put 0 in. In other words, we are going to find a y-intercept because 0 is in our domain. It's not one of the excluded values. So I can feel free and go right ahead to take f of x and put 0 in for x. And I have f of 0 is negative 1/5. So that means my y-intercept is the point 0, negative 1/5.